As an aircraft turns in the air, an undesired aerodynamical phenomenon occurs called adverse yaw. But to better understand adverse yaw, we must first understand the vortex that is created around the tip of a wing. According to Sheldon Green's Volume 1 Fluid Vortices, the large pressure differential between the wing pressure and suction surfaces accelerates fluid around the wingtip, thus producing a tip vortex. In other words, a higher pressure under the wing with a lower pressure above the wing produces a vortex near the tip of the wing as the air circles around from the higher pressure trying to get to the lower pressure. This means that as a winged aircraft begins to roll into a turn, the wingtip vortex induces a drag which opposes the direction of the plane. The drag is caused by the pressure differential in the vortex wake and the stagnation pressure at the front of the wing. Since the pressure difference above and below one wing is greater than the other wing in a roll, a greater drag is induced by the wingtip vortex, more so than the other wing. The imbalance of these pressure drags causes the plane to yaw in the opposite direction that the roll is trying to achieve, hence the term adverse yaw. As seen in this video, as the plane begins to bank left, a greater pressure difference forms above and below the highest elevated wing. This causes a larger vortex to form about the highest wingtip, which induces drag and the adverse yaw effect. Typically, rudders have been used over the decades to add stability into flight. Rudders are able to oppose the adverse yaw by producing another drag in the opposite direction. By inducing another drag, however, planes with rudders have reduced their efficiency by 60%, according to a study done by the NASA Aeronautics Academy in 2013. To increase aircraft efficiency and avoid effects of adverse yaw, a better solution was developed. Instead of fighting drag with more drag, the creation of the curved bell-shaped wingtip could counter and decrease the effects of adverse yaw. To decrease the pressure difference at the tip of the wing and reduce the size of the vortex formed, a curvature of the wing was created. As shown, the tip of the wing has an angled shape, while the root of the wing by the fuselage has a normal angle of attack. This means that more lift is created by the fuselage and less vortex-induced drag occurs near the wingtip. Due to the curvature of the wingtip, lift is faced slightly forward, meaning that a part of the force is in the direction of thrust. This forward thrust counteracts the effects of drag caused by the wingtip vortices. This small forward thrust is known as proverse yaw. Since proverse yaw counters adverse yaw due to the wingtip shape, no rudder is needed. Efficiency increases because drag no longer must fight against drag. Thanks to wingtip geometry and the laws of fluids, we can fly with ease.